Okay, in this example, we have another coupled system of 3 blocks that are in contact with one another, and they're on a frictionless horizontal surface, so no friction again, which makes this problem a little bit easier. A horizontal force is actually applied to mass 1, and we're going to take the masses to be 2 kilograms, 3 kilograms, and 4.8 kilograms with a force of 23.5 newtons. So the first part of this question asks us to draw a free body diagram for the system, which includes all of the blocks together, and then we're going to use that to find the acceleration. So essentially, we can imagine that everything inside of this box that I've drawn is part of the system, so even if the masses interact with one another, we don't have to worry about any of those internal forces. So my system has a mass of m1 plus m2 plus m3. Right? All of those added together, which is just 2 kilograms plus 3 kilograms plus 4.8 kilograms. So that's going to be 9.8 kilograms. So if I draw a free body diagram for my system, the only forces that I have acting on my system are this applied force of 23.5 newtons, of the force of gravity on my system, which is just going to be the total mass times gravity, and I have a contact force, which is the force of the ground on my system, right, which is acting up. And those are the only forces that I have. So if I choose a coordinate system where my x direction is to the right and my y direction is upward, there's going to be an acceleration of this system to the right because there is a net force acting to the right. So if I do the sum of the forces on my system in the x direction equals the mass times the acceleration of my system, the only force I have acting is 23.5 newtons. That's the sum of the forces that are acting in my free body diagram. And then the total mass is 9.8 kilograms and times the acceleration. So if I solve for the acceleration, I get 2.4 meters per second squared by dividing both sides of the equation by 9.8 kilograms. So I've used my system to determine what that acceleration is. Next, we're asked to determine what is the resultant or the net force that's acting on each of the blocks. And so the net force that's acting on each of the blocks is going to be acting in the x direction. So the net force on 1 in the x direction is going to be the mass of 1 times its acceleration in the x direction, which is the same acceleration that all of the blocks have. So the acceleration of 1 in the x direction is equal to the acceleration of 2, which is equal to the acceleration of 3, and they are all equal to 2.4 meters per second squared. So this is going to be 2 kilograms times 2.4 meters per second squared. So the net force on the first mass is 4.8 newtons. If I look at the net force on the second mass, it's also in the x direction, and it's just the mass times the acceleration in that direction. So this is going to be 3 kilograms times 2.4 meters per second squared. So the net force on mass 2 is 7.2 newtons. And then finally, the net force on mass 3 is going to be the mass of 3 times the acceleration of 3 in the x direction, which is 4.8 kilograms times 2.4 meters per second squared. So the net force on object 3 is 11.52 newtons. So the greater the mass, the greater the net force, because they all share that same acceleration. Okay, next we want to we'd like to know what is the magnitude of the contact forces between the blocks. And in order to do this, we have to draw a free body diagram for each of the masses individually. And then we can apply Newton's second law. So basically, if we go back up to our picture, there is contact between 1 and 2, and there's contact between 2 and 3. And because there's physical contact, those objects exert a force on one another. So for example, mass 2 exerts a force on 3. There's a force from 2 on 3, which is acting to the right on 3. And in turn, there will be 3 will push on 2, so there'll be a force of 3 on 2. In the same regard, mass 1 pushes on mass 2, and 2 pushes back on 1. Now, it's very confusing the way that I've drawn this picture because of the fact that, I'm not separating out the masses. But it is important to realize that the pairs of forces, these pairs of forces, are acting on different objects. They have the same magnitude but opposite direction. And in the same regard, I have another pair of forces here, which are acting on different objects but have the same magnitude in opposite direction. So if I transfer that down to my picture below, I'm actually going to start with mass 3. So as I go up here and I look at mass 3, I have a force acting on 3 to the right. This is the force from mass 2, which is in contact with it, and it's acting on mass 3. Yes, it's acting on mass 3. And then I also, of course, have a normal force. So I have the normal force from the ground on 3, and I have the force of gravity on 3, which is m3 times g. When I look at mass 2, I realize that I have two forces acting on mass 2. I have a force acting to the right, which is the force that mass 1 exerts on 2, but then 3 pushes back on 2, so I have a force acting back, which is the force of 3 on 2. And then, as always, I have this contact force, because it's in contact with the ground, and I have the force of gravity. Finally, I look at mass 1, and as I look at mass 1, the applied force is acting on mass 1, and that was 23.5 newtons. But then 1 is in contact with 2, so there's a force acting back from 2, acting on 1, and then I still have the normal force of the ground on that object, and I have the force of gravity. So we have separated out each of those masses, and we've looked at how they interact with one another through this contact force of the force of 1 on 2 and 1 on 3, or excuse me, 2 on 3 and so on. So now that we have our free body diagrams, we don't have to go back to our picture up here. We can just look at this in terms of the masses in the system. So if I look at, for example, the sum of the forces on 3, I'm going to choose to start with that one because there's only one force in the x direction. So the sum of the forces on 3 in the x direction have to equal the mass of 3 times the acceleration of 3 in the x direction. Well, we already found out above that this is 11.52 newtons, right? That's where we found this value right here, mass times acceleration. And over, if I look at my free body diagram, the only force I have acting on that mass is the force that block 2 exerts on block 3. So we have determined one of those forces. I can keep working my way back, and I can now look at the sum of the forces if I wanted to on mass 2. And the sum of the forces on 2 in the x direction has to equal the mass of 2 times the acceleration of 2 in the x direction. Above, we found that the sum of the forces on 2 has to be equal to 7.2 newtons, because that was the mass times the acceleration. And now as I look in my picture, I have a force acting in the positive direction, which is the force that block 1 exerts on 2, and I have a force acting in the negative x direction, which is the force that block 3 exerts on 2. So the force that object block 1 exerts on 2 is just the force that object 3 exerts on 2 plus 7.2 newtons. Now, according to Newton's third law, the force of 2 on 3 is the same magnitude as the force of 3 on 2. So I can put that value in, and I can determine what is the force of contact between blocks 1 and 2, and I get 18.72 newtons. If I wanted to check my results with rounding error, I could come over to my last picture and I could sum my forces here and make sure that it also makes sense here. So the sum of the forces on 1 in the x direction has to equal the mass of 1 times the acceleration of 1 in the x direction. We found that the mass times acceleration, the net force of 1 is 4.8. I see that I have an applied force in the positive direction of 23.5 newtons. And then I have a force from block 2 on 1 acting in the negative direction. So if I solve for that and I rearrange things, I get that 23.5 newtons minus 4.8 newtons is the force of 2 on 1. And basically this ends up being 18.7. And my pen just stopped writing. So the force is still going to be the same value there.